So for the last problem of the practice exam, we're going to look at if we can get it to get in focus here. Problem 3.11. We have a crate. It has a known mass. From that, we can calculate its weight. And what we're interested in, we're kind of seeing this assembly after the spring has already been stretched out in order to help counterbalance this weight. If you think about what's happening, though, we're going to again focus. This is very similar to a problem that we did in the Chapter 3 homework. We're going to focus on analyzing the equilibrium of this point of connection because if we were to segment it from its surroundings, it is acted upon by the force of interest, which in this case is the spring force. And in addition, if we draw a free body diagram at that point, we'll have three forces acting upon it, all of which are concurrent, so we can use a particle model. But what really is going on is if we focus on this point here, the weight is pulling it down, the spring is pulling it up to the right along this direction that's defined by the geometry. And this member, whatever that is, I don't think they tell us it's either a rod or a cable, but whatever it is, we know that the force that it is exerting is directed along the actual member itself. So oftentimes we'll talk about it a little bit more as we go on, but you call these forces that are exerted by supporting structures as reactions. So if I use that terminology, it's just kind of a general term for a force that's exerted by a support structure. So let's actually draw the free body diagram. And we're going to kind of separate this portion of the assembly from its surroundings. And what we would find is if we draw the effect of this spring, which is pulling it up to the right, and we draw the effect of this cable, which is pulling it up to the left, or rod, whatever it is, and we draw the effect of what this rod, which is connected to the actual crate, is doing, it's pulling it down. All three of those lines of action go through point D. So we have what's known as a concurrent force system. And whenever it's a concurrent force system, we can use a particle model, which means that we can basically ignore the underlying geometry of the body. What it really means is, we'll see when we get to the next chapter, is that the force system isn't going to cause any rotation about that body. It's just going to be purely a translational problem. So if I draw the free body diagram at point D, I have the weight of the crate pulling in the downward direction. I have the force that's exerted by the spring pulling along the direction of the spring. And I have the force that's exerted by that cable, or let's just call it a cable from now on, just that way I don't keep saying, oh, is it a cable, or oh, it is a rod. But it is directed from D to C, and it's a reaction force that's helping to keep this thing in the upward direction. So the question is, can we do any decompositions? Well, we know the weight is only directed in the negative y direction. And we know that if we're given the mass, in this case, it is 40 kilograms. We're going to use the acceleration due to gravity, which is in SI units, which is 9.81 meters per second squared. What about decomposing this? Well, clearly we don't know the magnitudes. However, can we do anything about the directions? Well, let's actually draw and see that if, and I'm kind of going to go up here, if this is the actual a side length of a triangle corresponding to the length of the spring, and this is going to be its stretch length, right? Notice that we're given geometrical information that we know how far that spring stretches in the horizontal direction, and we know how far it stretches in the vertical direction. Namely, this side length is 3, this side length is 2. So that means by Pythagorean theorem that this side length is 3 squared plus 2 squared, which is just going to be, 9 plus 4 square root of 13. So what that means is that if we define kind of the orientation of the spring by the angle theta, the cos of theta is going to be the adjacent side length divided by the hypotenuse, which is 3 over root 13. And the sine of theta is going to be the opposite side length over the hypotenuse, or 2 over root 13. If I do a similar thing over here, and I'm just going to kind of break this out again, what you'll notice is that this geometry, this side length is 2 and this side length is 2. So what that means is that this is a 45-degree angle. So you could do the same thing, but just a simpler way to write it, since you know it's a 45-degree angle, remember that for a 45-degree angle, the cosine and the sine are both the same, and they're just equal to 1 over square root of 2. So that means we can do these decompositions. Fs is going to have a positive x and a positive y component. It won't need adjusted. In order to get its x component, we would multiply the magnitude times the cos theta, but we know cos theta is 3 over root 13, and that's going to be multiplied by that unknown x component. The y component is going to be the sine of theta, which we know to be 2 over root 13. So that is an expression for actually decomposing Fs. And if we actually decompose FDC, notice its x component is going to be negative, but its y component will be positive. So we don't know the actual magnitude, but we do know that this angle theta, we would multiply by the cosine of it in order to decompose into the x component. We adjust the sine to be minus 1 over square root of 2. Don't know FDC. And then the y component is positive 1 over square root of 2 FDC. And again, these numbers are just coming from the cosine and sine of theta here. So if we enforce equilibrium in the x direction, in your book will sometimes show like an arrow to the right with a plus, and that just means we're calling forces that point in the right horizontal direction positive. So we're using a standard sign convention here. That x component, let's start with the positive one, the force of the spring, is 3 over root 13 Fs. That x component is minus 1 over root 2 FDC. The weight doesn't have an x component. And all this is saying is that the pull to the right of the spring must counterbalance the pull to the left of this cable DC. If we sum all forces in the vertical direction using a standard up positive sign convention, the y component of the spring force is 2 over root 13. The y component of FDC is 1 over the square root of 2. And in the downward direction, we're going to have whatever this weight is, which we need to compute, 40 times 9.81, and that's all going to be equal to 0. So here, we've talked about it beforehand, you have a system of very tightly coupled linear equations. So you can solve for FDC and you can substitute in, but as you progress through your engineering career, you'll really benefit from being able to have electronic tools to solve simultaneous systems of equations. So I'm actually going to write this in matrix vector form, since the majority of the tools that you use will likely require you to enter the actual system in that form. In equation 1, the first unknown, notice we have, we're going to make it in the standard form, but lining up the variables, the coefficient of Fs is 3 over root 13. The coefficient of FDC is minus 1 over the square root of 2. Coefficient in the second equation of Fs is 2 over root 13. Coefficient of FDC in the second equation is 1 over the square root of 2. So we call this our coefficient matrix. It's multiplied by our unknown vector. The first unknown is Fs. The second unknown is FDC. And it's equal to our constant term, which is all the constant terms in the equation. So the first equation, it's 0. And if I were to write this in standard form, in the second equation, I would have an mg. So I'm going to go to whatever tool you like to actually solve this electronically. I'm going to use MATLAB. I'm going to define my coefficient matrix. The first row is 3 over the square root of 13. That's 1, 1. The second element in the first row is minus 1 over the square root of 2. In the second row, I have 2 divided by the square root of 13. And the second element is 1 over the square root of 2. I'll echo it to the command line just to make sure I don't have those numbers memorized, but at least the signs look correct. I'll define my constant vector. First row is 0. Second row is the mass times the acceleration due to gravity. So 40 times 9.81. Looks like that. And the way you solve simultaneous equations in MATLAB is just by that special kind of division. So you don't have to worry about that. You don't have to use MATLAB. Use whatever calculator technique you want to solve a system of simultaneous equations. And if you want to solve it by hand, more power to you. Definitely feel free. But eventually you'll find that you'll benefit from having a way to solve systems of equations, especially if you think about it. When you get to like a 3x3 system, right, that's going to be a real big pain. And your book kind of gives you the majority of 3x3 systems are pretty loosely coupled, so you can solve them easily through substitution. But for the 2x2 systems, they rarely give you that. So these quantities are both in newtons. So is that, like, are we done? Well, we're definitely not done, because what we have, this is the restoring force of the spring. But that's not what we wanted. We wanted to know how much the spring was actually stretched. So if you think about it, and particularly we didn't want to know how much the spring was stretched. That's the problem that we did on the homework. We wanted to know how long was the unstretched length of the spring. Well, remember that the way that Hooke's laws works is that the restoring force is proportional to the actual displacement of the spring, and that is its stretched length minus its unstretched length. So we know the restoring force is 282.9637 newtons. We know the spring constant is 165 newtons per meter. So that's going to allow us to solve for L minus L naught. So I'm just going to solve for L minus L naught, and then we'll adjust and actually find what the unstretched length of the spring was. So that's just going to be 282.9637 divided by, and I'm ignoring the units for now, 165. And that'll come out in units of meters, of course. So I'm going to take this, and I'm going to divide by 165. And that's going to tell me that the spring in this case actually stretched out 1.7149 meters. And I know that the actual, in this case, I know the stretch length of the spring is the square root of 13. And I got that from above. Remember that it would help if you could actually see what I was writing. But we solved for the stretch length of the spring originally in order to decompose this geometry. So since it's the square root of 13, what that means is I can actually solve for L naught by just taking the square root of 13 and just, I'm doing some algebra in my head here, but subtracting away that amount of stretch. And if you do that, what will you get? Let's take the square root of 13 and subtract away the answer. And if you round that to three significant figures, you'll get 1.89. And of course, that's going to be in the native units of length for the problem, which is just meters. So hopefully that made sense for you, and good luck on the first exam. Do reach out if you have any questions.